Hypothesis testing really applies tools that we've been using throughout this course. I mean, this goes all the way back to calculating means, finding a proportion, knowing what a sampling distribution is, confidence intervals, z-tables, t-tables, all those basics, they're coming together now. So what do we do in the case of hypothesis testing? Well, it's really a 4-step process, and we'll cover the first 2 steps in this lecture. Key. Hypotheses have to be collectively exhaustive, mutually exclusive. I mean, if these hypotheses are not mutually exclusive, then it would be possible to get a value of a statistic that would occur in either one of the hypotheses. What do we do? Well, the answer is we don't know what to do, because it seems like we're either agreeing or disagreeing with both hypotheses at the same time, and it can't be. They have to be collectively exhaustive. We have to cover all our bases. We cannot leave gray areas. We cannot leave values where we don't know what to conclude if we had the misfortune of obtaining such a value. So we have to cover all our values, and we have to have hypotheses that don't overlap. Okay? Now once you get past that, what do you got to do? Well, you really got to decide, are you going to use a 2 or a 1-tailed test? The key here is in a 2-tailed test, it's about different, changed, not the same as. In other words, direction doesn't matter. What's important is whether something is different from what we think it is, not whether it's more or less. That tells us 2-tailed test. When you're reading a problem in a book, that's a dead giveaway as to how to form the hypotheses. If they say different, if they say not the same as if they say change from, 2 tails. 1-tailed test, direction matters. So you're looking for directional clues. Does it matter if something's bigger, smaller, greater, less, more than it used to be, not as large as it once was? Those things tell you 1-tailed. Now the easy hypotheses, frankly, to form are 2-tailed hypotheses. We always form hypotheses about parameters. So suppose we think the population mean is 10. Then a 2-tailed test would be a very simple one. HO, the null hypothesis, the base case would be mu equal to 10. Alternative hypothesis, mu not equal to 10. It's that simple. The equal to sign is always in the null, the not equal to is always in the alternative. So those are easy. It's the 1-tailed that tend to give people more trouble. Well, the way I've tended to attack this is a skeptical approach. In other words, somebody walks into my business and says they want to sell me something, and they promise my result's going to be more than 10. Okay, null hypothesis, it would seem on face value would be, well, of course, then we should use the null greater than or equal to 10. But think about it. That means you believe somebody that's selling you something. Is that really the way you want to attack a problem like this? My approach would tend to be, boy, you're promising me more than 10. I'm going to go with less than or equal to 10 for my null hypothesis. That way I take what you say with a degree of skepticism. My alternative is greater than, and then I'm looking to see if I have enough evidence to reject the null and accept the alternative hypothesis. Okay? The skeptical approach. I'm looking for evidence instead of simply believing what you say. Okay? So if you'd walked in and said, I promise you this will be less than 10, my alternative and null hypotheses would be clear to me right away. Null hypothesis would be greater than or equal to 10, alternative less than. Again, skeptical approach, I'm looking for enough evidence to reject the null. I'm taking a contrary point of view to what you say rather than agreeing with you. Also keep this in mind when you form 1-tailed tests. The equal to part of the test is always in the null. In other words, the null will always be either greater than or equal to or less than or equal to. The alternative hypothesis cannot have an equal to sign in it. The alternative hypothesis would always be greater than or less than. Again, that gives you mutually exclusive, collectively exhaustive hypotheses and grounds your null hypothesis with the equal to sign. Okay? Now, a quick and dirty rule that I've always used historically, and I found this very helpful when I'm reading questions in a book, and I'm not quite sure how they're attacking the problem, is this one. I look at the sample mean and I compare that sample mean to the hypothesized population mean. So if my hypothesized population mean is 10, then what's my sample mean? Well, suppose it was 8. If it were 8, then my alternative hypothesis would be less than. Now, what's my rule? Answer, sample mean x bar, less than 10, alternative less than. I use this little rule to decide my alternative hypothesis, and of course, therefore, my null would be greater than or equal to 10. So if my sample mean is less than the hypothesized parameter, I use less than for the alternative. Suppose again my parameter is thought to be around 10, and I find my sample mean is 15. My alternative hypothesis would be greater than. In other words, my sample mean of 15 is greater than my hypothesized population mean of 10. My alternative hypothesis is greater than. My null, of course, therefore, would be less than or equal to. What that does is force the sample mean into the tail that we'll later call the rejection region. It forces it in that direction. It doesn't necessarily put it in the tail, doesn't necessarily cause us to reject the null, but at least it gives us a chance to reject the null. I mean, think about it. If your sample mean is 15 and your population mean is thought to be 10, and you form a test where the null hypothesis is greater than or equal to 15, or greater than or equal to 10, and your sample mean is 15, wouldn't you automatically accept the null to begin with? In other words, you have no real test. So again, it sort of lines up with this idea of being skeptical that if my sample mean is above this particular value, I put that on my alternative hypothesis and I use that to see if I have enough evidence to reject the null hypothesis. Okay. Now, once you get past the basic formation of hypotheses, and I remind you, because I'm obviously focused on means here, this is very simple. If you're dealing with proportions, two-tailed test, p equal to some value, p not equal to the value is my alternative. One-tailed test, much the same as before, p greater than or equal to some value, p less than or equal to some value. For my null hypothesis and my alternative, if p is greater than or equal to 0.5, my alternative would be p less than 0.5. So these rules apply to proportions just as well as they do to means. Second step of the process is determine the statistics you want to use to conduct the test. Well, this is actually to some extent very simple. If it's a question about means, my statistic is x bar, duh. If it's a question about proportions, my statistic is p hat, duh. As you get to regression, you see it can get a little more complicated, but that's a little bit down the road. The second step's a little harder, but we've already done it, so it can't be too hard. You have to decide whether you're using the z or the t-table. Well, simple. We use exactly the same rule we use for confidence intervals. If the sample size is less than 30 and the population standard deviation is unknown, we're using the sample standard deviation, then it's a t-test and a t-table that you use. That simple. Exactly the same rule as before. Everything else is going to be z. Obviously, if you're dealing with proportions, it's a z.